So in chapter 4, we're going to be studying mostly quadratic functions since we skipped over the linear part since we've done that earlier. So section 4.4 is going to be building quadratic models. So that's equations that tell you about something real that's happening and try and describe it in a mathematical way. So we're going to build quadratic models from verbal descriptions, and then we're actually not doing this part from data. That's objective 2. So the first objective that we're going to be working on is just what the title says of build quadratic models from verbal descriptions. So the objective is the title of the section. So we're first going to look at some economics and business applications, and these are really important for everybody to understand because most people end up working for a business in some way of some kind, and so it's helpful if you understand something about how the money part works. So if we talk about revenue, that's the dollars that are coming in to the company from doing something or selling something. So if the things you're making, whatever they are, they're selling for P dollars each. Okay, so each one costs P dollars. Then if you sell X of them, the revenue function, and we write R of X, will be P times X. So this always happens, right? If you have the per each and you want to know a total, you multiply. If each one costs $5 and you have 10 of them you sell, you multiply the 5 and the 10 to find out how much money you make. So the quantities P and X are related by something called the law of demand. So if you've studied economics already, then you've heard of this, otherwise maybe not. So the equation that relates the quantities, the price, and the number you sell is called the demand equation. So often the demand equation is linear, so the revenue equation then is quadratic. So let's look at an example where here is the demand equation. So you're given the demand equation. And personally, I think the economists think backwards, but this is how they do it. They say that the price depends on how many you sell. I would say how many you sell depends on the price, but I'm not an economist. So if they drew a graph of this, they'd say when X, the number sold, is 0, so if X is 0, P is 1,000. So this is P, the price, each. And then they say it has a negative slope. So it's a line with a negative slope. Well, that kind of makes sense because if when I'm charging, say, $500 and I'm selling whatever this number is, then it does seem to make sense that if I charge more, like if I charge $750, I would sell fewer because it costs more. And so this describes how people behave as the price changes. So they're thinking of it from the business's point of view, though, where the business is trying to decide what the price should be based on how many maybe that they can make or that they want to make. So let's find a model. So that means an equation, a mathematical model that expresses the revenue as a function of X. So we said on the previous page that revenue equals P times X. So now we take this expression that's equivalent to P and we put it in here in place of the P. And we see that we get negative 1/3 X squared plus 1,000 X. So this is the revenue function. So this is in dollars. Because price is in dollars each. And then X is in number of units. So this is total dollars, if you like, of the total income from selling that many of the product. So this is going to be a downward opening parabola, we can see, right? Because the leading coefficient, the A, is a negative number. So the domain of R is all real numbers because a polynomial can have any real number put in there. But if X is standing for the quantity sold, then really that doesn't make sense. So really we need to just have from 0 and up, and those are really the only numbers that make sense. And in fact, we can solve for this point here of what happens when the P is 0. What is the X? So I'm going to add 1/3 X to both sides and get that X equals 3,000. So really this number of 3,000 is the end of where the graph makes sense. So you'd have from 0 to 3,000, and it doesn't make any sense to have more sold than that when the price would become a negative number, which really doesn't make any sense at all. So these demand graphs are always in the first quadrant only, and then the revenue graphs only make sense in the first quadrant only. Actually, revenue can be negative, I take that back, but it needs to be positive values of X. So the domain is from 0 to 3,000 are the only values of X that make sense. So the C part says, what is the revenue if 100 units are sold? So that's saying if you sell 100, what is the revenue? So I want to see the proper notation for a function, and we put 100 in for the X, and then we'll figure out what that is in class together. So then they want to know what quantity maximizes revenue. So I want to maximize R of X. Well, it's a downward opening parabola, right? So the max is going to happen at the vertex. So we can figure out where the vertex is. The X coordinate is going to be minus B over 2A. So it's going to be minus 1,000, the coefficient on the X, with a negative, over 2. A is negative 1/3. So that looks like 1,500 to me. So when 1,500 units are sold, the revenue is maximized. So that's the X value at which the maximum revenue occurs. So then it says, what is the maximum revenue? So the maximum revenue is going to be R of 1,500, right? So it's going to be negative 1/3 times 1,500 squared plus 1,000 times 1,500. And we'll calculate that out together and find out what is that maximum revenue. And then the E part says, what price should the company charge to maximize revenue? And let's do that part together in class. Okay, the next one I just want to talk about a little bit, but I want to do it together in class. So this is a really typical kind of maximizing or minimizing problem where you have 3,000 feet of fencing. So 3,000 feet. And you want to use it to enclose a rectangular field. Well, there's lots of different shapes that will work. You could have 1,000 and 1,000 and 500 and 500, right? And that would work. But you also could have 1,250 and 1,250. It's not a very good picture. And 250 and 250. So there's lots of different ways this could work. So we want to try and figure it out with math of what's the best thing we could do. So we have this 3,000 feet of fencing, and we want to make a function that's the area of the rectangle as a function of x. So the area of this rectangle would be 500 times 1,000, right? And the area of this rectangle would be 250 times 1250. So I want you to come up with two other examples of rectangles that would work, that would use the 3,000 feet of fencing, and see what the area is. And then we're going to do the math way of doing it. Okay, and then the last one we're going to look at is a physics type problem, analyzing the motion of a projectile. So I talked about this the other day, of if you fire something from a weapon or a water balloon from a slingshot or whatever you want to think about it, if the angle is 45 degrees to the horizontal, so that means this angle is 45 degrees, so diagonal, with a muzzle velocity, so that means when it's starting, it's getting shot out at 100 feet per second, and that's only important it shows up here. So then the height of the projectile, so this is the height at this point, this is the height at this point, this is the height at this point. So the height is modeled by this equation that says where x is the horizontal distance. So this is x, here's where you're starting, and so this is the horizontal distance. And we want to know at what horizontal distance is the height of the projectile maximum. Well, sure enough, again, it's the vertex. So we're trying to find the x coordinate of the vertex, which is h. So it's minus b over 2a. So it's going to be the opposite of 1. The coefficient on the x is 1 over 2 times the a is negative 32 over 100 squared. So that looks kind of crazy, but we can do this. So we have a negative and a negative, so that we don't need to worry about. It's going to become positive. And then this fraction is going to turn upside down because we're dividing by a fraction. So we actually multiply by the reciprocal. So then 100 squared is 100 times 100, and this is going to be over 64. So this is the x coordinate where the vertex happens. So this is the highest point of the projectile is going to happen when x equals this number. And then to find the maximum height, it's going to be, and this is confusing that this is h, this is the vertex hk. Let's make this one capital H. So capital H of 10,000 over 64 says plug in 10,000 over 64. Well, that looks awful, but we can do it. We have calculators. So we plug in 10,000 over 64 for x in the first term, and plug in 10,000 over 64 for x in the second term, and do the computation, and that will give us the maximum height of the projectile. Then it asks us, at what horizontal distance from the firing point will the projectile strike the ground? So we're talking about this spot right here. I'm going to let you think about that for a little while of how we could find that point. And then we'll make this graph together. So that's it for this section.